So data science community has a dedicated Slack channel. You can explore our job section. We also have a dedicated blogging section, and and you can also involve to explore our resources or to donate to a Women Who Code program, as well as expand your leadership skill. You also have a dedicated section for companies on global partnership, and we also offer scholarships. Don't forget to join our micro content blog or micro content platform on Beacons. So here we have our speaker, Professor Nimrita Koul, and over to you, Professor.
Thank you, Kritika, and hi, everyone. Welcome to this session. I'm very excited to be here with you all today, and we are going to look at two projects, two case studies, one on a sentiment analysis using transformers and another one on building a chatbot, again using transformer model. I'll quickly share my screen and yes. So you all should be able to now see my screen. We introduced transformer models in the last session, last Thursday, and we spoke about how transformers are deep neural networks. They have proved to be extremely powerful in natural language processing, as well as computer vision also. And of course, I think all of us are stumped by the performance of ChatGPT 3 and now ChatGPT 4, and a number of models which are coming up every day, the transformer models. So we are going to build two transformer models today, one for sentiment analysis and one for question answering, or one for conversational AI. We'll start with sentiment analysis. Just before we start with today's session, here's a quick recap of what we already covered. In session 1, we saw an introduction to natural language processing, its tasks, components, applications. We also saw many Python libraries which are used for NLP, primarily NLTK, Spacey. Then we also worked with PyTorch. And today we are going to work with Transformers library from Hugging Face. In session 2, we learned about different techniques, different tools for text pre-processing before the text can be used with ML models. We saw about cleaning, normalization, tokenization, removing stop words, lemmatization, stemming, and some other techniques. We also learned in session 2 about how to convert text into numerical form using techniques like bag of words, TF-IDF, and word embeddings like GLOW and Word2Vec. In session 3, we learned about text classification, and we had an introduction to transform models. So in session 4, we are going to do in-depth case study for sentiment analysis and chatbot using transform models. All right, let's get started. So sentiment analysis is a very well-known technique in NLP, and it all boils down to recognizing emotional content or subjective information from a piece of text. You can do a detailed or fine-grained sentiment analysis where you identify a big spectrum of emotion, like something is extremely negative, something is extremely positive, or just negative, just positive, or neutral, and so on. So there can be many shades of the sentiment that you can identify using the sentiment analysis technique of NLP. What is the general flow of steps that is involved in an NLP project in general and in sentiment analysis project in particular? It all begins with collection of data, a relevant data set in text. You do the cleaning, data pre-processing, then you do feature extraction, you convert the text into numbers, into the vectors which can be fed into ML model. You do feature extraction, identify the relevant words or relevant sentences, and then you train an ML model on these features, and then you deploy your ML model. You use it to make the predictions. In the case of sentiment analysis, the prediction is about labeling the sentence with what kind of sentiment is primarily depicted in that sentence. There are different types of sentiment analysis as they speak of. There is fine-grained sentiment analysis where you identify a huge spectrum of sentiments. There can be emotional detection where you are not identifying the satisfaction levels, let us say, of from the product reviews. You are identifying the emotions of somebody who is interested in listening to some music based on emotional states, analysis of emotional states. There are some recommendation systems which prescribe what music you can hear and so on. There is also a flavor of sentiment analysis which is called intent analysis, which means trying to identify the intention behind some text. What is it that was in your mind when you wrote that review, or what is it actually that you want to convey through that text? And then there is aspect-based analysis, which focuses on specific aspects of your review. For example, you are speaking about a product, a camera, let us say, in your review, and you're saying the camera is great, but the battery life is not very satisfactory. So in this particular review, we automatically want to identify that the customer has a good sentiment about the product as a whole, but the concern is about its battery life. There are lots of applications of sentiment analysis, primarily in the business field, where companies want to keep a track on the pulse of the customer base, and in governance, where of course governments are interested in keeping a track of how the citizens are feeling, what is going to be the result of next election, and so on. So that this is quite an important application of natural language processing. All right, so we are going to do this case study using BERT. BERT is a pre-trained transformer model from Google. The full form of the acronym BERT is Bidirectional Encoder Representations from Transformers. I remember in the last session, somebody asked, we did not answer it last time because, I had already planned to speak about it in detail in today's session. So BERT actually is a transformer model which does not contain a decoder part. It is made up of stacked encoders only. So we'll see a bit of detail of BERT's architecture today. So it's a bidirectional encoder representation from transformer models. It's a masked language model. What is the masked language model? We'll come to understand today. So BERT actually has the pre-trained representations of all the words and a lot of words and sentences in English and a few other languages. Now, there are certain models which are non-contextual. That means they remember or they learn the representations of text, every word in text, but every representation is independent of the context, which means the model learns how to represent a word without it having any bearing on the word following it or the other word which precedes the current word. Such models are called context-free models, and GLOVE and Word2Vec or fast text, which we studied about in the previous session, are context-free models. But the representations learned by BERT are contextual, which means whenever it learns to represent a word in a sentence in numerical form, that representation has the built-in information about what was the word following this word and what was the word preceding this word. So here's an example. For example, I accessed a bank account. So the word bank here refers to a financial institution, right, where we do our monetary transactions with. And there can be another sentence which also has the word bank. For example, I went to a river bank. So in this case, bank refers to the bank of a river. And in both cases, you can disambiguate the meaning by context, right? A bank account word specifies or helps you disambiguate the meaning of bank. And in other sentence, the word river helps us disambiguate the meaning of the word bank. So by accessing context of a word, by trying to correctly ascertain the meaning of a sentence from the context is what makes BERT and other transformer models so powerful in learning and generating language so accurately. So here's a brief comparison between the architecture of BERT, GPT, and Elmo, which again is a deep transformer model for language representations. So we see here that the sentence we pass in as an input to the BERT, at every layer of BERT model's encoder architecture, the representations are passed in both the directions. They are passed from starting word in the sentence to next word, and from last word to the previous word and so on. So your BERT model gets to see the sentence from beginning to end as well as from end towards the beginning. That way, the context information is encoded into the representation for every word in the sentence. Now, BERT framework has two steps. It has a first step, which is called pre-training, where the embeddings and representations for the words and sentences are learned and given to you when you download a pre-trained model. And the next step is fine-tuning, where you actually add an additional training part to your pre-trained BERT and make it ready to work for your specific NLP task. Like, for example, I have a model, I have a BERT model which already can do a bit of question answering, and then I can fine tune it with my specific data set, and it can become a question answering bot for example, for my medical data or for my data which is related to the course I'm teaching at the university. So the BERT model is pre-trained on unlabeled text data, which means the text, it is unsupervised learning. When you initialize, when you pre-train BERT model, all the parameter weights are learned and they are given to you. And during fine-tuning, those parameter weights can be upgraded or updated. And this upgradation can be done for all the layers or for some specific layers. In this diagram on the screen, we are looking at the architecture of BERT for sentence to sentence, where a pair of sentences is fed as input for tasks like question answering or machine translation, conversational AI, or text entailment detection or paraphrasing. So what we basically are doing here, we are feeding in two pairs of sentences. We are feeding in pairs of sentences, two sentences, sentence A and sentence B. And the model learns to predict whether sentence B is the sentence which should follow sentence A in the actual input data set, in the training data set or not. This is called a next sentence classification. And this model also uses masking, or, because it's called masked language model, which means at every step during pre-training, it also tries to predict certain words from within a sentence. Those words are masked and the model has a task of predicting those masked words. The overall performance of this model during pre-training is a sum of the objective function of how good it is at predicting the masked words and how good it is at predicting whether the next sentence is the correct sentence which should follow the sentence A or first sentence. So here is the pre-training part. You have sentence A, you have sentence B, which is fed as input to of your BERT model's encoder structure. Both sentences A and B are masked, which means some words out of the sentences are masked. They are replaced by a special token called mask. So the model does not get to see the entire sentence. Then these sentences are passed through text pre-processing, tokenization, encoding layers. And finally, the model learns to make a correct prediction regarding the masked words. It also learns to make a correct prediction regarding whether the sentence B is the sentence is a sentence which actually follows sentence A in the training text and so on. So this happens during pre-training. And then when you're fine-tuning this model, you are showing it the smaller data set, which is specific to your application, which is specific to your NLP task, and it updates the weights of the already learned or pre-trained transformer, and it gets ready to do the task of question answering or paraphrasing for your specific problem, your specific domain. So what are the input representations in case of your BERT model? The input representation for a pair of sentence is as a single sentence. There are specific tokens which are used to represent the beginning of a sentence. There are specific tokens which are used to separate two sentences of a pair. So that is how BERT combines two sentences of a sentence pair into a single sentence, into a single input sequence, passes it on to first layer, and thereon computes the attention scores, passes on the results to the next layer, and so on till we get the final representations of our text. Here's an example of how encoding happens in case of BERT. So we start here at the input layer. This is a sentence, my dog is cute. The other sentence is he likes playing. So the sentence is always, the beginning of the sentence is marked with a special token CLS. And here the word dog is masked. It's replaced by a special token called mask. In sentence 2, see the SCP token here separates sentence 1 from sentence 2. And this SCP token again indicates the end of two sentences. So here again, the word likes is replaced by mask. So during pre-training, your BERT is trying to predict these words which have been replaced by mask. And it is also trying to predict whether this sentence here is the correct following sentence after this sentence in training data also. So this input sentence is converted into token embeddings. There is also information regarding sentence embedding, which is made a part of the embedding, which means there is some way of indicating whether this word belongs to sentence A or B, whether this word belongs to sentence A or B. So this information is called sentence embedding. After these two embeddings, the token-wise embedding and the sentence-related information, there is some way of also incorporating the information related to the position of the word in the input sequences. Together, these three embeddings help the transformer to represent the input pair of sequences in the form of numerical vectors. Here's an example. This is an input sentence, a visually stunning rumination on love. This is first broken into the individual tokens, and then those tokens are fed in with the BERT related special tokens, CLS or separator, and then they are converted into numerical values or numerical indices. We will see how this is done in code also in a moment. So during pre-training, BERT has been pre-trained on book corpus and Wikipedia with a together of around 4,000 million words. And during pre-training, as I spoke, it's a masked language model. So around 15% of the tokens in input data are all masked. And then BERT tries to predict what is the correct word that should be replacing that masked token. So here's an example. The man went to it has been masked. He bought a mask of milk, right? So perhaps, yeah, our answer here for this mask should be store. The man went to the store. He bought a gallon of milk. Then after this layer of embedding and everything, we finally have a classifier layer at the end of BERT's encoder block. This classifier layer can be a spot vector machine or a fully connected neural network with its specific activation function, and maybe a normalization layer or addition layer. And output of this classification layer is generally given by a softmax function, which gives a probability score for every word which can be used, which can be predicted by the model to be the next word in the sequence. The word which has highest softmax score is actually outputted as the next word completing the sequence. So in the next sentence prediction task, again, as I told you, we have data input where there are sentence pairs which are fed to the pre-training BERT. These sentences consist of 50% sentences where sentence B actually is the next sentence of sentence A. And there are 50% sentences where sentence B is not the sentence which should be following sentence A in the training data. So your model has to predict whether sentence B is actually next sentence or it is not the next sentence. During fine-tuning, we are using self-attention mechanism. Of course, self-attention allows BERT to learn the joint representations of both input sequences A and B, and it also allows it to perform much better as compared to previous models which were unidirectional or which did not use contextual information. Here's a brief comparison of model sizes we have available for BERT. The BERT model comes in two sizes, BERT base and BERT large. BERT base has around 12 encoders, BERT large has around 24 encoder blocks with 110 million and 340 million parameters respectively. So since this is a transformer model, there will be an attention layer, a self-attention, a multi-headed attention layer. There will be a addition and normalization layer. And then there is a classification layer using a deep feed-forward neural network. We also have BERT, which takes care of cased letters. Cased letters means it's case sensitive and it is non-case sensitive. There is BERT for other languages, also, for example, French, Arabic, and multilingual BERT. And there are certain variants to BERT architecture like Roberta, Distelbert, and Albert. And of course, there are lots of AI tech, lots of NLP tasks that can be done very comfortably, that can be done very efficiently with BERT. Sentiment analysis being one of them, conversational AI, question answering, paraphrasing, text generation, text prediction, and finding out whether and disambiguating the word sense is also one of the applications of BERT. All right, next we are going to look at a small sentiment analysis case study where we will be using Twitter tweets. It's labeled data set. So you have the tweets by many people and you have the corresponding label also. We will be, this is called Smile Annotations final.csv data set. You can download the data set from here. I think we have also shared the file now with you. So the first step in every program which deals with data is to, of course, first to load the data in a format where it's comfortable to work with. We'll be using pandas data frame to store our data set, and then we'll be doing pre-processing on this data set. We begin with the imports, required imports. We use read CSV of pandas to load our CSV file into a data frame DF. You can see the data has two columns. It has 3 columns, ID, text, and sentiment, but will not be using ID column, so just dropped it. The 2 columns are text, which includes the text of the tweet. And the second column is sentiment, which has many values, no code, which means the sentiment is not available. Then there is happy, sad, disgust, anger, and so on, we'll see. So here we are looking at how many unique types of sentiment have been labeled to the tweets in this data set. In around 1500 rows, the sentiment is not available. In around 1100 rows, the sentiment is happy, not relevant, angry 57, surprise 35, and so on. So just by looking at this these counts of sentiments, we can decide that, these are very, very less, just one row with sad or disgust or angry, 2 rows with sad or angry, and so on. So we'll just drop these sentiments which are very less in number. This can be done by extracting all the rows which have the sentiment containing an or this pipe character, and then we'll only retain the sentiments which are happy, not relevant, angry, surprise, or sad. After doing this filtering data, our data set now contains only the tweets where the sentiment is either happy, non-relevant, angry, surprise, or sad. You can see that the sentiment column here is categorical, which means it contains text. So we will convert it into numerical form using a label encoder from sklearn. We pass the sentiment column to label encoder, it converts it into numbers. So what exactly it does is it finds out how many unique sentiments you have. To each sentiment, it assigns a number, it enumerates the sentiment column. So here are what sentiments we had and what numbers have been generated for them. So angry is represented by 0, happy by 1, not relevant by 2, sad by 3, surprised by 4. After doing this conversion of categorical label column into a numerical column, we'll go ahead and do text processing on the tweets also. For that, we are using this function called process text. And what exactly this does is it normalizes the text, which means it replaces or it removes all the non-static characters. It removes all the words which begin with a digit. It removes all the punctuation marks. It converts all the words into lowercase. It removes stop words. It lemmatizes the words. And here is what our resultant text looks like, right? Now, this text does not contain any special characters, non-square values, or punctuations, and so on. Next step is to split this data, which consists of tweets and their labels, into 2 portions, training portion and test portion. We have used a split of 75:25, which means if my data set had 1000 rows, then 750 rows will be used for training, and the remaining 250 rows will be used for testing the evaluation or testing the performance of the trained model. So that's what we do using train test split, which is imported from sklearn's model selection module. Now we have 4 parts to our data: X train portion, X validation portion, Y train portion, and Y validation portion. Next, we will have to build a model, and that model is coming from transformers library from Hugging Face. So you should have transformers installed on your computer. You can do it from the Python prompt. You can also do it right from your Jupyter notebook using pip install. Use an exclamation mark before pip because this is a system command. So exclamation mark pip install transformers. They should install this library called transformers on your computer. Once it is installed, you can go ahead and import the required modules from this library. So what I require in this program is BERT tokenizer, which will tokenize our input sentences and convert it into a representation with which BERT can work. We will also be using PyTorch library here for converting our input in a form in tensor data set format, which is a matrix-like format or a tensor format with which your BERT model or transform models can work easily. So we import these 2 libraries, and then we go ahead and create an object of BERT tokenizer. This is BERT tokenizer from pre-trained, which means we are loading the pre-trained BERT tokenizer. This is an uncased BERT, and it will do the lower casing for us. Although we don't need it, we have already done it during pre-process. So the object of BERT tokenizer is called tokenizer, and then we want the data to be converted into the specific sequence formats with which your BERT can work. That means the beginning of the sentence should be represented using the token CLS, and then it should insert the separator tokens wherever the sentences break, and so on. All of this housekeeping chore is done by a function called badge encode plus for us. A badge encode plus function is built into the tokenizer. So here is what we are doing. We are calling the badge encode plus function on xtrain and xval. It converts our text into a representation. It encodes our text into a representation, which is familiar to the BERT token, the BERT model. So there are so many parameters that we pass to these to this function, and they are very. I mean, they have a very specific purpose here. For example, here we want to say that we want to add special tokens to our input. To encoded input, the special tokens mean CLS, SEP, and so on. We want this encoding function to return the attention masks for input. We also want to increase or pad our sentences to a maximum length we want all sentences to be converted into a fixed length format, which is done by padding the missing words with zeros in the output encoding format. So that's what is represented by this parameter, pad the sentences to a maximum length. And if some sentences are already longer than the max length, then we have to truncate those. And what is the maximum length we are allowing for this case? It is 256 words. And what should be the return type of the tensors? They should be the tensors that can work with Python. Our transformers library can also work with JavaScript. So this is to specify that we are working with Python tensors in this case. So this encoding is applied both to the validation data set and the training data set. And here's what your tensor looks like. It's all numbers. The text has been represented as numbers. If you want to see the data type of this, you can just do type and data type. This will show you that your data now is in a format called batch encoding. And then we are going to convert it into long tensors, which can be done using a torch.tensor. This converts your encoded numbers into a specific matrix representation, which is tensor data set. So now we have, after running this cell, two tensors, tensor underscore train data, tensor underscore validation data. So now our input data is ready, encoded, and in the form in which a BERT can work with it easily. So
Professor,
next thing,
sorry to interrupt, before we
yes,
jump to the pre-trained session, we have few questions to be answered.
Yes.
There is a question saying BERT can also be used to classify text into categories similar to sentiment classification. Could that be done?
Yes.
Okay.
Sentiment analysis is classification.
There is one more question pertaining to the unsupervised task mentioned about BERT.
Yes.
There are two pre-trained unsupervised tasks, masked LM and next sentence prediction.
Yes.
The question is what makes them unsupervised? Don't we have the original sentence as the ground truth or label?
No. There is no human supervision involved. Although the training data we use, for example, a Wikipedia page, right? Naturally, your sentences are have an order there, right? But there's no supervision involved. You have sentence A following sentence B. So in that sense, it has the information regarding original ordering among the sentences, but there's no explicit labeling done by experts.
Okay. There is one more question pertaining to the sentiment analysis. Can we keep the emoticons?
Emoticons, yes.
Yeah, emoticons could be kept?
Yes.
I think we are good now, Professor. We can proceed.
Yes. So now we are going to actually fit our BERT model. So far, we imported BERT tokenizer, which enabled us to convert our text into the numerical representation and the format in which BERT is comfortable to work with. Now we are downloading and installing. Now we are actually loading the pre-trained sequence classifier from BERT. This class is called BERT for sequence classification. You have to import it from transformers library. Again, it is a pre-trained classifier. It is BERT uncased, and how many number of labels you want it to output. It is equal to the number of unique labels in your data set. Do you want extra outputs from your model? For example, attentions and hidden states. In this specific example, we do not want them. So this is how we created an object of pre-trained BERT for sequence classification. The name of our model is BERT model. Next, we are going to create data loaders, which means we are going to feed our data into the BERT model by batches, in mini batches. That exactly can be done using a built-in class, which is called a data loader. This is available in Torch utils module. So using data loaders, we can divide the input data, both training data and validation data, into smaller batches, which are randomly selected from the overall data. And then we are ready to use these loaders or batches of data to train our model. The one important thing we need to just speak about in this case is about optimizer. We know that when we do classification or when we train a deep neural network or any ML model in general, we update the weights during backpropagation or during updating the gradients. We change the weights so that our loss is minimized. This is called optimization. We have, I think many of us know about the optimizers like gradient descent or stochastic gradient descent. The optimizer we use with BERT is generally Adam optimizer. And this optimizer comes with weight decay or without weight decay. Weight decay is about change in the learning rate. Would you like the learning rate to be constant throughout the training process, or would you like the learning rate to vary? So sometimes it helps to converge faster if your learning rate is varying. So that's exactly what we are doing here using a scheduler. Scheduler algorithm helps you to modify, to change your learning rate among the training epochs, between the training epochs. So Adam W is the Adam optimizer with weight decay, and we are using a learning rate scheduler, which helps us to manipulate or change the learning rate of the algorithm during the training epochs. So we are importing Adam W from transformers. We are also getting the linear schedule from transformers library. You create an object of both here using the name of the class. You pass it the parameters, the name of the model you want to be optimized. You pass a default learning rate or a beginning learning rate, and you also specify how many epochs you want. Create the object of scheduler, which necessarily tells you how the learning rate will be changed over the number of iterations of this algorithm. And then we are going to code the training loop. We initialize certain seeds, which help you to recreate the results when you run the same file next time. You also specify whether you're going to use a GPU machine or a CPU machine. And yeah, here is our function for evaluating our model. This is the model name and eval. During this evaluation function, we are not going to update the parameters of your model at all. This is just an evaluation of the performance of your pre-trained BERT, which you have imported directly from the transformers library. What exactly we are doing here is we are feeding it some data, and we are just checking what is the performance, what is the F1 score, what is the overall accuracy, and what is the overall loss of your model for the pre-trained BERT without any fine-tuning. And of course, you will see that this pre-trained BERT does not work very well with your specific data. So we are going to fine-tune it. For the fine-tuning step, we are again going to use BERT model, but now in the training mode, we are going to update the gradients of it, certain weights. We are going to change the weights of certain nodes in this neural network. We are doing gradient clipping in this case to change the gradients to prevent it from having explosive gradients or exploding gradient problem. We will call Adam optimizer and the Adam scheduler, the rate scheduler, to vary the rate after one epoch of training. And this will go on till the number of iterations you have specified as a hyperparameter. You can save this model after every epoch of pre-training to your hard drive, and then during evaluation you can load any of these fine-tuned models and see its performance, as we will also see in this program. So when you are training your model, you are essentially updating the weights of certain neurons of certain layers of your pre-trained model based on the specific data set you have right now in the problem at hand. So we trained in this specific case for 3 epochs, and we noticed that as you increase the number of epochs, your loss will come down and the performance or your F1 score will go up. So once we have fine-tuned our BERT, we will be using it to make some predictions, to do some sentiment analysis. So for that, we are again loading the fine-tuned model into a new parameter or a new variable called BERT model. This is BERT from sequence classification model. We are loading it to, we are identifying the device from which you are loading it. In my case, it is a CPU machine. If you are using a machine with GPU, then you will be using that particular form of BERT, which will be optimized to work with parallel functionality, parallel cores that are there with GPU. Once you have created a BERT object, you are loading its parameters, its new weights. So that can be done using the function load state dictionary. And now you are loading the fine-tuned BERT with which has been fine-tuned for 3 epochs, right? So here you have to be very observant regarding what kind of fine-tuned BERT you are using. So when you are saving during fine-tuning, you are saving it epoch-wise. I have done only 3 epochs of fine-tuning, so I'm loading the model which has been fine-tuned till epoch 3. And this is from my CPU machine. This model now is the model which is fine-tuned for my specific data for 3 epochs, and I'm using that model for evaluation now for predicting the sentiment labels for my training, for my validation data. The result of this model is here in the variables predictions, which are the predicted labels or predicted sentiment values, and the true labels or the sentiment values which are actually there in the labeled data set. And then I am plotting the performance of my model in the form of a confusion matrix and a classification report. So for all the sentiments which are represented by 5 classes, 0, 1, 2, 3, and 4, like angry, happy, sad, disgust, and so on. So I can see what is the precision, what is the recall, what is the F1 score, what was the average accuracy. So we can see it was not much, just 78%. Maybe if we train it for more epochs, the accuracy will go up. So here's the confusion matrix for all of the 5 sentiment classes. I can see what was the true label and what was the predicted label. You can see for this particular sentiment, the number of true labels and the number of predicted labels is actually matching. And it's not that much for other categories, for other predicted and true labels. So a simple example of sentiment classification using BERT fine-tuning for Twitter sentiment analysis. I will be moving to a second case study, which is a chatbot. Are there any questions we need to answer right now?
There is a question asking like, what is the error efficiency of BERT, and is that calculated in the total model error evaluation? They just want to find out if there is an
for
if it is
multi-class classification, like this one, where your output labels are multiple. It's not just 2 labels, happy and sad. There are multiple labels. We do not do an accuracy score. We generally do a class-wise prediction, class-wise accuracy computation. So for 5 classes, for every one of the class, how many were correctly predicted? So that's captured by a confusion matrix or by F1 score, instead of having a single accuracy number.
Okay, there is an added question. Is it calculated in the total model error evaluation?
Total model error, this is F1 score. F1 score is a balance between precision and recall parameters. So in a way, you can say, yes, F1 score, a single number F1 score is a representative of how good your model is.
Yeah, that is all for now, Professor.
Yes. So I will stop sharing this and I will share another Jupyter notebook. Is that okay? Just one moment.
Yes, please.
Is my screen shared with everyone? The new screen?
Not yet, Professor.
Okay, let's give it a moment. I think it should be shared by now.
Yes, Professor.
Yeah, great. So now we are looking at second case study, which is building a chatbot. And this is a full encoder decoder architecture, which means while BERT did not have a decoder, this has a decoder, a full-fledged decoder. And instead of just one, it has kind of 2 decoders. So let's see what it is. This chatbot and in general, any question answering model in NLP is a sequence to sequence model, which means we are feeding it in a one sentence or one sequence, and the output is another sentence or sequence. So it transforms an input sequence into an output sequence. That's the reason that these models are called transformers. So before current transformer models, we used to have recurrent neural networks or LSTMs, or GRUs, which are the variants of recurrent neural networks, and they had the special ability to remember the word which comes before the current word, and that helped them to work well with the tasks related to text data, like which is sequence-based data. So a sequence to sequence model is also called as encoder decoder architecture, which means there is one set of deep neural network architecture which is called an encoder, which is fed with one sequence, and it performs, like we just spoke about, it performs embeddings, encodings, and then embeddings, and converts your input sequence into a representation which has the information about not just the current word, but also the neighboring words or the context. This information in the form of hidden vectors is fed to next layer, and that layer has access to previous word and the word behind that and the word preceding that, and so on. So these networks, these encoder decoder, this architecture has proved to work very well in case of natural language processing tasks like machine translation, paraphrasing, and language generation. So this is an example which represents the meaning of a sequence to sequence task. We have here a sentence in English: the weather is nice. It's fed into an encoder, which is made up of LSTM units. LSTM is an RNN block with a little, with a bit of additional, change in circuitry with respect to gates, and which are capable of remembering for a longer sequence length. So we are feeding in a sentence to this LSTM encoder, and then it converts it into internal representations, remembering for every word the previous word, and of course the current word, and then creating a context vector, passing it on to the decoder, which has its own context vector also. And the decoder's task is to predict what will be the next word. Given the current word, what will be the next word in the destination, in the target language. For example, if we are speaking about machine translation task. Again, we see that it uses special tokens to indicate beginning of a sequence and end of the sequence, and so on. So what exactly happens is that at every step, the decoder has the task of predicting the next word or even the next character for generating the correct output sequence for an input sequence. And then this continues to happen till we reach a special sequence or special token, which is called, for example, stop, at which point you know that the decoder network knows that your input sequence has been converted or transformed into the required output language, or it has been summarized or paraphrased, or you have found the correct answer to the input question, and so on. So this example that we are going to look at is the standard documentation from PyTorch, and this chatbot works with Cornell movie dialogues dataset. This Cornell movie dialogues dataset is a huge dataset which has around 220,000 conversations between 10,000 characters of movie characters, and a lot of utterances, around 3 lakh utterances, 9,000 characters, and 617 movies. It has two main files, movielines.txt and movieconversations.txt. There's a special format used for storing data since these are text files. So what is the format of data stored in movieconversations.txt? It's stored like this: user ID 1, followed by this special pattern which separates two fields: user ID 2, first user, second user, those who are having the conversation, field separator, name of the movie, field separator, and the line IDs. What are the line IDs covered in this conversation file? So this is the format of every line in movieconversations.txt. Other file, movielines.txt, contains the actual text, actual lines which are spoken between the characters. So the format is line ID, separator, user ID, separator, movie ID, name of the user, and then separator followed by actual text, what the user actually spoke. So during this program or during this code, we will see how to load that data and then how to convert this data into the format where your transformer can actually be trained on it. So required imports, we're using PyTorch. So you have to import PyTorch. I'm assuming that it is already installed on your computer. And I'll be using a CPU. And in case you have a GPU available, your device will be a GPU. We import our data. You're free to have your data files in the folder in which you're working. You can also store it in a special folder called the data and with a corpus name, kernel movie dialogues corpus and so on. Depending on how you save your data files, you will access them by specifying correct paths in these functions. So we have some housekeeping functions here. This is a function print lines, which just helps you to print the line by line content of your file, movie lines.txt. So we see this is what the text looks like. Then we have a load lines function, which loads all the lines from your movie by removing the separator character. So this separator character will be dropped. We have load conversations, which loads the data from movie conversations file field-wise. We have extract sentence pairs function, which extracts the text, the sentence pairs from the conversations by movie underscore conversations.txt files. So with these three housekeeping functions, you can read your input files and you can extract only the text pairs from them, conversations from them. And then we are now going to convert these conversations into simple running text, the sentences following each other without any markers of field ID, character ID, movie ID, and so on. That is what we get when we run this cell. So here is your text, the sentence with the following sentence, next sequence, and the sentence following it, next sentence, and the sentence following it. So in a way, this is our training data in text format, human readable format, where we have sentence A or sequence A followed by sequence B and so on. Now we are going to do further pre-processing on this text. For that, we are going to create a class called VOC. Class VOC's job is to create a vocabulary out of your input text. Vocabulary means all the unique words in your text and all the sentence pairs in your text. This class VOC has functions like add word, add sentence, trim. The add word function adds a new word to the set of vocabulary words. Add sentence adds a sentence from your input file to the sentences list of your data. And the trim function removes all the words which occur very infrequently. And then we are going to have a few more functions for text pre-processing. For example, Unicode to ASCII removes non-ASCII characters. We normalize the string, we convert it to lowercase, we remove any characters which are beginning with digits, we strip our input string of all the spaces, extra spaces, and then we convert it into the set of vocabulary and the set of sentence pairs. We filter all the sentences which contain rare words. Rare words are the words which occur infrequently. We remove all these sentences which contain rare words. We also drop the words which are rare. We also drop the sentences which contain rare words. And after this, we load the final data set, which contains the vocabulary and which contains the sentences where the words are only from the vocabulary. That means there are no infrequent words. This content is now stored in the form of our training data ready to be fed into our transformer model. So the sentence pairs are what we have right now, a list containing 2 sequences, 2 sentences. This is the housekeeping function which removes the rare words from our training data. Now we are doing something to the data which makes it usable with the transformer model. So that means we are converting words into numbers, and then we are bringing those numbers into a format, into a standard length or fixed length by padding them with zeros. We are converting them into a binary matrix format. For every input sentence pair, we are converting it into a binary vector format or a binary matrix format. The result is something like this, where you have a matrix of numbers, and we also have the matrix of lengths of every tensor. And then we'll go ahead and define the model that we are going to feed this data into. Our model here is a bidirectional multi-layered GRU or gated recurrent unit, which essentially means this, that your model is capable of reading sentence from beginning to end, and also at the same time from end of the sentence to the beginning of the sentence. So it gets to see the entire context of every word and is able to learn the bidirectional representations just like BERT. So what is the flow of code that is going to happen here? We are converting word indexes into embeddings. Word indexes means simply representing words with numbers, but these numbers are not in the fixed length format. They cannot be fed directly into the transformer. So we are converting them into embeddings with token embeddings, sentence embeddings, and position embeddings. This involves padding your word sequences with zeros if required. Then we do a forward pass through our encoder. We may require to unpack the padding, and then we perform the sum of every layer within our encoder and return this as a context vector to next layer, and so on. This is the implementation of encoder part of our RNN, which is using a gated recurrent unit. And then this is the decoder architecture, which uses self-attention mechanism. With self-attention, we are essentially trying to combine the context of sentence 1 with sentence 2 and pass it on as context layer or as a hidden state vector to next layer of the decoder, so that a decoder can decide correctly what word to predict, what next word to predict, given the previous words in the input sequence. So this is the implementation of attention layer. This is Luang. There are two types of attention primarily. This is the Luang attention layer implementation. And here is our decoder architecture, which is based on this Luang attention scheme. So it essentially implements a forward layer in which the attention is calculated for every input you get from the encoder, previous encoder, and also based on the previous context vector of the decoder itself. Finally, it uses softmax to find out the probability of all the words possible as next words, and out of that, the word which has highest softmax score is predicted as the next word completing the sequence. The loss function this architecture uses is called masked loss instead of using simple accuracy or simple cross entropy loss. So the training function here is actually setting the gradients to 0 in the beginning and then updating the gradients of every layer. You can run this training procedure, depending on how many iterations how many iterations give you a comfortable score, or how much resource you have in terms of compute. So I have trained it for 4,000 iterations. You can decide for how many iterations you want to go ahead and work. How comfortable is how accurate is the answer that your chatbot is generating for your input query. So after you implement this training procedure, which does a back propagation and updates the weights of your model, you are ready to go ahead and evaluate your model. For evaluating your model, you essentially use an evaluate function. And before evaluate function, I just want to speak about this greedy search strategy that decoder uses. In some transformer models, they go ahead and implement the teacher forcing, which means you will force the decoder to use the target word itself as the predicted output, which is not always the best way out, which always does not give the very correct output in conversational AI problems. So a simple search or a greedy search is to use the word which has highest softmax score. That exactly is what this greedy search decoder class implements in this code. We are implementing a greedy search decoder, which is a wrapper on top of our decoder, Luang decoder, which we already implemented above. This enables you to pick the word with maximum softmax score out of at every layer of the decoder. And then we have written an evaluate function. The task of evaluate function is to take the input sequence or the query sequence from the user. When the user is chatting with the bot, that sentence the user inputs is called a query instance. It converts that query instance into indexes and then converts it into tensors, which can be fed into the model, and then it applies the greedy search. It runs it through the encoder network, decoder network, applies the greedy search to find the best word, and then outputs that word to you. So we are running this evaluate function in an infinite loop, and the output you see is an input box or a text box in which you can chat with your model. The model keeps on throwing a response to you. This can go on happening till you are satisfied with your model. So we are running this training module here, where the initialization of encoder, decoder, optimizer, the learning rate manipulation, everything happens. Then training iterations run. We have run it around 4,000 times, and you can see the loss keeps on coming down as the number of iterations increase. So we stopped at 4,000 iterations with a loss of around 2.03. Then we are going to evaluate our model using the evaluate input function. So here is where you can enter your query or your interaction with the bot. And here is the response that bot generates. This is in an infinite loop, so it will keep on going on till you enter a specific word, for example, quit or queue or buy, and which is a cue for the bot to stop conversing with you. So you can see from this that some responses are okay, but some responses could have been a lot better, right? Which signifies that our training data could be better, or we could increase the number of iterations, or maybe our architecture could have been a little different. We could hyperparameter tune this model to increase the conversational ability of a model a little bit. So yes, are there any questions? It's 19:59 here, and
No.
I'm done.
No, Professor.
Great. So, all right, can we close then? Shall I stop sharing my screen? Okay. Kritika, are you there?
Yes, Professor.
Okay. All right. So can we close? I'm done.
Oh, yes. There is one more question asking about the courses and offerings that is provided from your end outside of Women Who Code, so that participant would gain out of your knowledge and experience.
I don't as such provide a course, but through Women Who Code or through PyData Global, I keep on sharing. I keep on delivering sessions and workshops and tutorials. But yes, I'm actually planning to have a course on Coursera soon on natural language processing using transformers. So why not? I'll definitely inform if somebody, meanwhile, you can be in touch over LinkedIn so that whatever comes up is known to you, is shared with you.
That's wonderful, Professor. Participants, please be in touch with our community, as well as please be in touch with the professor for updates on the new Coursera course, as well as on further communication that would be provided by the professor. So yes, we are
Thank you so much, everyone, for joining these sessions. And I look forward to you doing some good work and letting me know, what did you build, how it helped you. And that'll be really great.
Yes,
and thank you to the wonderful team of volunteers at Women Who Code for their effort, for wonderful organization. Thank you, Stephanie, and everybody who has been with me for these 4 sessions.
There is already shout out pouring for you, Professor.
Thank you so much.
Yeah.
All right. Bye-bye then. Have a good time, everyone.
Bye, everyone.
Bye.
And
I will stop the recording now.
Please don't stop the recording. Yeah. Yes,
Oh,
Siddhi?
okay. Yeah, I haven't.
Yes.